All right, let's begin. Today's problem is a very interesting one. How many five-digit positive integers exist where the digits are non-increasing from left to right? For example, 87743 and 10000 fulfill the conditions, while 78987 and 33429 do not. Well, the first thing we should do after reading our problem statement is just figure out the very important parts. We are required to have a five-digit positive integer, and the digits are non-increasing from left to right. That's the premise of this problem statement. We have four examples. These two examples seem to satisfy our problem, while these two examples don't. And we can see this pretty simply. In the red examples, the ones that are underlined in red, the digits increase from left to right for some two digits. For example, in 78987, the first two digits are 7 and 8, and that's an increase, which is not allowed in our digits, or in our integers that we are supposed to find. Similarly, the digits in the 33429, they increase sometimes, for example, 3 to 4 and 2 to 9. That is not allowed. So let's try to find a mathematical formulation for our problem statement. We have five digits, D1, D2, D3, D4, and D5. Now, how do we make the non-increasing restriction mathematical? Well, we'll be using inequalities. Take D1. For the digits D1 and D2 to not be increasing from left to right, D1 must be what? Greater than or equal to D2, because D1 cannot be less than D2, or else that would constitute an increase. Similarly, if we consider the two digits D2 and D3, we'll find that D2 must be greater than or equal to D3. And this inequality chain grows. D3 is greater than or equal to D4, and D4 must be greater than or equal to D5. And this is the single most important equation that we'll have in this problem. It pretty much is the problem itself. We have five digits, and the digits are non-increasing from left to right. Very important. Now, let's take a look at some of the examples. We have 87743. We'll notice that 8 is greater than or equal to 7, which is greater than or equal to 7, and so on. Same thing with our number 10,000. That one also works. Immediately, we can notice that we can repeat digits. The greater than or equal signs allow for this because of the equal section. So what we can do here is make a very interesting realization. That's one of the two most important problem-solving techniques that we'll use in this problem. I'll explain it to you with an example. Say we just choose five random digits. Let's choose five random digits. Let's say 2, 3, 9, 8, and 6. With these five random digits, we are going to try to make a five-digit positive integer that satisfies the conditions of the problem. Now, how are we going to do that? We know that t1 has to be the greatest integer, or else it'll constitute an increase from left to right if the digit to the left of it is less than it. So the first digit has to be 9. Similarly, the next digit has to be 8, because if it's after the 6, 2, or 3, that'll be an increase. Moving on with the same logic, after that must come 6, 3, and 2. You'll notice that this is the only combination of the digits, or the only ordering of the digits, that yields a number that is a five-digit positive integer that satisfies the problem statement. That's very interesting. Is this a one-to-one relationship? We can choose another set of five digits, for example. Let's choose some repeating digits, 5, 5, 5, and 7, and 0. Now, what can D1 be in this case? Again, we're trying to make one of the five-digit integers that satisfy the problem statement. Well, the first digit must be 7, because if it goes after any of the other digits, that would be an increase. After that, we must have 5. We must have the other 5s. Then we have to have the 0. This is another forced sequence. You must order the numbers in this way to get a five-digit integer that satisfies the problem. And so this is a one-to-one relationship. It's very interesting. All we have to do is choose five random digits, order them together in only one certain way, and we'll have an integer that satisfies the problem. Due to this one-to-one relationship, we're able to formulate our problem and rewrite it pretty much. We can rewrite it in very simple terms. How many ways can we pick five digits? And we can specify that the digits are 0 to 9. Now, there are some interesting restrictions that we have to this. Let's take the five numbers that we chose randomly at first, 23986. We can't pick something like 3, 2, 6, 8, 9, for example, because those constitute the same five digits. We need to pick five different digits, and we want to find the number of ways that we can do that. We'll notice that because of the one-to-one relationship, this question in red that we rewrote is almost exactly equivalent to our original problem statement, bar one important exception that I'll talk about later. And so we'll try to think about solving this red problem now. Now, one problem solving technique that is very useful in this kind of situation is stars and bars. I'll assume that you've heard of stars and bars and that you've maybe used it once or twice, and that you know the premise of it. We have some stars, sure like that, and then we have some bars. Sorry, bars, and then they look like that. Now, what we want is the bars to separate distinct groups. And what kind of groups can we have here? Well, we know that we have 10 digits, so why not let those be our groups? Let's draw 9 bars to separate each group of digits, like this. We'll say like the first digit is going to be 0, it's over here, and so on all the way to 9 at the very right. And these bars will separate the groups of digits that we'll place our stars into. And what will the stars be? These stars will be digits. And we'll have 5 of them. Of course, we have 9 bars, as mentioned earlier. And so what we do is pretty much, since we have 5 digits, we'll just place them between the bars in the digit groups. In our example over here, 23986, we'll have one digit at 2, another at 3, another at 9, another at 8, and another at 6. You notice that there's no repetition here, but let's take the 55570. If we draw another set of 9 bars, then the 55570, there would be 3 stars in the 5s, 1 star in the 7, and 1 star in the 0 bin. And so you notice that any combination of these stars and bars, of course, 5 stars, very important, or sorry, yeah, and 9 bars. Sorry, I'm getting mixed up with 9 and 5. Um, any ordering of these 5 stars and 9 bars constitutes a picking of the 5 digits. This is another one-to-one relationship. Let's just run through another example, this time picking the stars and bars instead of picking the number. Let's put 3 bars and then a star, 2 bars, 2 more stars, 3 bars, 2 more stars, and then 1 more bar. That's 5 stars and 9 bars. What number does this make? This makes, let's see, 0, 1, 2, 3. That's a 3. And then 4, 5. That's 2 5s. 6, 7, 8. That's 2 8s. And 9. Remember that the stars are the digits and that the bars separate the boxes of digits. And so that is our number. And again, furthering this point, we can just make this into one of the numbers that satisfy our original problem statement. And there's only exactly one way to do that, and that is 88553. Again, having that one-to-one relationship. Now, it's just up to the ways that we can order the 5 stars and 9 bars. How many ways can we do that? Well, this is a pretty simple permutation or combination. It's just the total number of objects, which is 5 plus 9, 14. Choose the number of stars, which is 5. You could also choose the number of bars, which is 9. Those give the exact same number, which is 2002. So after all of these one-to-one relationships, don't we think we are done? Well, I mentioned one exception earlier, and that is the exception 0, 0, 0, 0, 0. Very important, sometimes especially easy to forget about this exception. If we have all 5 stars here on the left at 0, we'll get a not 5-digit number. It's just 0. It doesn't work. And this is the only exception because, for example, if we just change one of these digits, let's just change the last digit to a 1. This actually works because as soon as we rearrange the digits, 1, 0, 0, 0, 0, to satisfy our problem statement, just like we did down here, it's a very, very 5-digit number looking positive integer. And so that 0, 0, 0, 0, 0 is the only exception we have to this rule. This is the only thing we have to subtract off from our 2002, yielding a final answer of 2001. And so there are 2001 5-digit positive integers which have the digits non-increasing from left to right. Thank you.